Hello again. This is now lecture 7.1, where we're going to talk about some other kinds of work. So actually there's a pretty good and probably more complete description of this in your book than we'll do today. In section of the second edition, 2.9, so that's page 30. Sorry, 2.9, page 28. I think it's section 2.3 in the third edition, or chapter 2.3. So on other kinds of work. So what we've mainly talked about is, so far, changing the volume, right? That's our example of a piston. But last time we also talked about changing the length of a wire, right? So those are both discussed in that chapter. So that's like stretching a string. So you also talk about magnetizing, right? A material. So you can imagine taking a magnetic material and magnetizing it. And there the work would be B times dm. So this is the applied magnetic field. And this is the magnetic moment. Now, M is the magnetic moment, which is defined as the magnetization times the volume. So this is the magnetization. Okay, so this only works for things that are paramagnets. So let's remind ourselves, if you don't remember about magnetism, there's a few kinds of magnetism. There's paramagnetism, which means the spins will align, the moments will align in the same direction as the magnetic field and be proportional to. So that's what we're talking about here. There's diamagnets, where it's exactly the same as this paramagnetic, but they oppose. So the magnetic moment will be minus, so this could be negative. So this could work for diamagnets as well, but there'll be a minus sign here. But there's also so-called ferrimagnets, anti-ferromagnets, and ferromagnets. And for those, this kind of description will not work. And that's because this is assuming that this process, called it a work, is reversible, right? So just another reminder that our work has to be reversible, right? We weren't talking about dissipative work, we were talking about configurational work. That is, it was reversible. We could change the configuration and then change it back. But not dissipative work. So not friction, but also not ferromagnets, because ferromagnets have a hysteresis. So most people, when they think magnet, they think ferromagnet, actually. So, but most things aren't ferromagnetic. Actually, only iron, cobalt, and nickel are. Actually, only iron and nickel are the only two ferromagnetic elements, and nickel is actually an anti-ferromagnetic. Then various combinations, steel and various alloys will be can be ferromagnetic, but actually it's a very small subset of metals that are ferromagnetic. So mostly when people are thinking of magnets, they're thinking of steel or iron, or nowadays, these neodymium iron boride. But you can hear again they had this iron in them, right? So they're iron alloys. So those are the little tiny ones that allow you to have tiny speakers these days. Okay, so that doesn't count for those because they are permanently magnetized along one direction. So that means that if I applied a moment a magnetic field, those moments wouldn't change direction, right? Or they wouldn't change direction easily. Okay, so this does not count for that. A little easier is to think about, so this is, let's call magnetic. So we can think about electric fields, right? So an electric is actually a little easier to think about because the work will be just very similar, an electric field and dP. So this is the electric field. And this is, it's called the dipole moment. Many of you have probably taken chemistry classes where you think about like the electronic orbital and distorting it, and then there's a dipole moment. There's a net electronic distribution. You can even do this in solids, right? We can apply an electric field and displace some of the charges one way and some of the charges another way, and we'll get a dipole moment. So this is related to the dielectric constant, epsilon, which goes like 1 plus the electric susceptibility. So that's an electric field susceptibility, and that's going to change the polarization which is going to be P, which is simply going to be E times the electric field. Or another way to say it is E0 times the susceptibility times the electric field. Great. So this is the dielectric constant for free space, and this is the susceptibility of a material. All right, so that gives you a dipole moment, P, which is that polarization times the volume. And you can see that's kind of a similar thing. There's a magnetization times the volume, and this is the polarization times the volume. And you get a magnetic moment, and you get a dipole moment. Luckily, there are no ferroelectric materials, right? But so this is a much more so generally, this kind of system will be reversible, right? So again, as long as it's reversible, there actually are some ferroelectric materials, but they're very, very rare. Okay, so another one that the book talks about is a battery, right? So you could imagine having a battery where you charge up a battery, right? And it has, it charges and discharges reversibly, like a recyclable battery, right? The battery in your car, like a chemical battery, can be charged and discharged reversibly. You could not allow a current to flow, right? Say through a resistor, because as soon as you have I squared R, you have a dissipative work. You've had some resistance. I think the book also gives an example of a stirring, right? So a stirring is a form of dissipative work. So the book also talks about surface tension, for example, of a soap bubble or the film of a soap, stretching it out. So this is actually kind of in between the case of the changing volume and the tension or the stretching of a wire. It's actually changing the surface area of a film. So we've talked about charging a battery, dielectric materials, magnetization. So the point is that we can think about configurational work in any of these examples as being reversible, right? And you can somehow relate to a gravitational work, right? Okay, what do I mean by that? So the very simplest thought of way we can do work is we can take an object and we can raise it, right? We can take a book, we can raise it, we've done some work, we've taken an object, we've moved it through some distance dx, the integral of f dx. It would be constant if I did it constantly, and be non-constant if I did it non-constant. I'd have to do that integral to find the work. I can release it, and it's reversible. I can actually do the same things with these kinds of works. I can actually equate them to a gravitational work. I can actually imagine taking, for example, a mass, right? And I can imagine turning a generator. Right, take a mass on a pulley. So let's see. Let me draw it a little bit better. So you can imagine taking a mass on a pulley, right, and have that pulley connected to a crankshaft of a generator. So let's imagine this is a pulley, and this is a crankshaft. And this is a generator, and out of a generator comes, for example, a voltage, right? A voltage difference. So let's have this one attached to ground, and now you can imagine, for example, running an inductive loop, which would generate a magnetic field. So this is actually how, this crankshaft and generator is the alternator in your car, right? It takes the motion, or actually even nowadays, even more so with hybrid vehicles, right? You're taking that energy back from the rotation of the wheels. You're turning it into along a crankshaft, and using a generator to create power. And then that's going back to your battery. So that's actually exactly how the regenerative braking on a hybrid vehicle works, right? It's actually engaging this generator when you apply the brakes. It doesn't actually push off like dissipative work like you used to, right? Now it actually engages, say, the magnets of a generator. All right, so now you can imagine that I had turned mechanical work into this form of magnetization, right? Similarly, I could have a capacitor plate, right? And that would form an electric field. So, and theoretically, right, if I magnetized a material, then I could actually demagnetize that material, and the generator could turn that back into the mechanical work. I could pull up the mass. So it's like charging and discharging a battery, charging and discharging a magnetic moment, or a change in polarization. Okay? So all of the forms of configurational work should be interchangeable. So that's the key concept there. Okay? Now the key thing here is that this is, I showed you an inductor or a capacitor, but I did not show you here a resistor, right? So an inductor or a capacitor is okay, but as soon as you have a resistor, it's not okay, right? So now if you were to generate your power, your work, which would now turn into a current, which would be dissipated in an I squared R, so this is an R, and then the power is I squared R, right? The power dissipated is I squared R. Then that's not okay. That was dissipative. Right? And we told you that we can't really yet define this dissipative work. Right? We don't have a mechanism in our so far conversation about work to understand what dissipative work is. So dissipative work and like a resistor is not included in our discussion. Okay, so we're going to pause here and we're going to go on to lecture 7.2, where we're going to start to explore what is this dissipative work.